introduce you. So Furong Huang is an assistant professor from the computer science department at the University of Maryland and a visiting research scholar at Capital One. Her research focuses on trustworthy machine learning, sequential decision making, and foundation models for perception and control. She has made foundational contributions to world model learning, alignment of generative agents, and robustness in vision language systems. She's here to present on from perception to action, world model learning for generalist agents. Yep. Over to you, Frank.
Thank you. Thank you for the introduction, and thank you for having me. Sorry, I couldn't be there in person, but I'm sure you guys are having a blast over there. So yeah, so I'm Furong, and today I'm going to talk about my recent, sort of work on world model learning for generalist agents from perception to action. So how do I make a good foundation? What makes a good foundation model for sequential decision making or for robotics specifically? I sort of made a wish list, and I thought that most people will agree with me that this foundation model should be versatile, should be generalizable, should be resilient. So I guess there's not much debate about how important it is for pre-training to be very diverse and including a lot of tasks, so that you can have this versatility for downstream tasks and algorithms. But what about generalizability and resilience, right? So I feel the community may have a lot of debate about it scaling up all you need, specifically for sequential decision making and robotics. Which is very different from natural language processing and computer vision. Maybe another question that we'll try to answer a little bit is next token prediction all you need for solving sequential decision-making problems and robotics? Well, so I want to start by saying that although these foundation models we have are remarkably successful, nowadays, they were unfortunately not very data efficient, right? So if you look at Llama 2 models, it was trained on 1.4 trillion tokens, which is unfortunately 3,800 times more tokens than a human would have verbally exchanged at the age of 50. But will we ever run out of data, right? So that is the ultimate question here. I guess a lot of people agree that pre-training is basically like a competition about, data curation. You create all the data, you have more compute, you have better hardware, better algorithm, larger clusters. Is your data growing, right? We say that the pre-training of these foundation models is basically using internet to fuel these language model training. But are we going to run out of data? Right, so let's take a look at this Llama 3 model. Let's say that we're gonna take that as a reference point and call that as one llama in terms of the number of tokens it was pre-trained on. Now, if you think about GPT-4, rumors is that is about half a llama, which is what is it trained on, although we don't know. But now if you look at that scale and look at the data we have, if you look at the fine web data, which is exactly at the boundary of one llama, right? And then if you look at non-English web data, it is also exactly at the boundary of one llama. So indeed, we're right at the boundary where we are using up all the internet we have. So, but if you look at these models, well, here I'm just taking some llama models here to show you the training loss, right? So as the models get larger and larger, and the performance have not saturated yet. If you look at this curve, you can see that there is still room for improvement if you supply this large language model training with more tokens. Well, so indeed, if you think about robotics, there's even more challenge, right? So what is the fossil fuel of robotics? Is it only, is it data from the internet? It is also, the kind of collected data that we have to actually, like spend a lot of human labor to collect, right? We joke is like human fueled data, right? For robotics, humans only have 24 hours, and you can only at most collect 24 hours of data if your collection is very smooth, right? So, and now if you think about the diversity in robotics and all the cross embodiments, right? Different embodiments that you can imagine, then the kind of data you need is probably massive, right? Considering all the diversities out there. Now, so indeed, I would claim that we are still in a very small data regime for robotics, even if we believe that there is this remarkable success in NLP or computer vision, that scaling up is all you need because we have the luxury of all the data we have from the internet. I doubt whether we will have the luxury of just scaling things up in robotics, giving all these variations in robotics. And that's why I'm claiming that we're still in the small data regime. Now going back to the foundation models for sequential decision making, right? So just think about the entire pipeline here, that you have data collected from diverse tasks and domains, and you build your foundation model, you have this transformer architecture or some other more advanced architecture that you would claim it's better, or not necessarily. There's still a lot of debate there. Now you go through some forward paths and you have some pre-training objective function. All right. And then the real question I want to ask here is, what should this pre-training objective function be, such that through backpropagation, you're able to learn this foundation model in a data efficient manner? As we just talked about, we're still in a small data regime. And for robotics, right, specifically, how can we utilize a better pre-training objective function so that we can train things in a more efficient manner? All right, so now let's take a look at, whatever you observe as the observation from this environment that you're interacting with as an agent or as a, kind of robot. So this observation usually has to go through some kind of encoder. You get some latent representation, and this observation is very crucial for you to make a decision, because that's the information that you're getting in terms of making that decision. Now, once you make that decision of the specific action, as the previous speaker was also talking about, then you could potentially do this transition dynamics rollout if you have a world model, right? If you have a world model, you could do this rollout. You could try to predict what the next state will be given this action. And you can even be smarter about not predicting the noisy observation space, but predicting the more compact latent space, and therefore, resorting to this kind of latent world model. Now, based on the next state, you could continue the rollout, right, using your world model, imagining taking another action, going to another state, and so on, until you reach the final state or final time, right? So you could potentially be given a reward. Sometimes these rewards are there, or sometimes they're not there. It could be a sparse reward, or you could be even in a very kind of like a no reward situation. Now, so what's really nice, if you have such a world model, and essentially, because we're in RL conference, this is essentially this transition dynamics, right? So model-based reinforcement learning. Now, with this world model, you were able to plan ahead through this imaginary rollouts. That sounds really good, right? So that also means that you may not need so much data if you are able to learn such a good world model, right? So now the question here is, can we somehow, rather than do next token prediction, figuring out a training objective that learns a good latent world model, right? So that is the question I wanted to ask here. So I sort of claim that this will really help in terms of the generalizability and resilience using this world model in this latent space. If we're able to find a good latent space, right? in the RL community, we're all familiar with this kind of like representation learning, right? If we're able to find a good latent space that is sufficient and necessary for planning and for, predicting the transition dynamics, and very likely this kind of latent space will be a fantastic representation of some common, basic laws of physics, for example. It's basically like a set of rules of how the world actually work, right? So based on that motivation, we sort of did a line of work along this way, and not explicitly learning this world model per se, but to utilize these world model idea and this latent world model idea to sort of guide our pre-training objective design. So for example, I'm going to start with tackle, which is a temporal latent action-driven contrastive loss. What tackle does is very simple. Let's say, given us, you have this trajectory in your training data, right? And you are, trying to learn a latent representation such that you're able to do world model prediction under this latent representation very well. Okay, so now starting from an observation, you go through a state encoder, get a latent representation of the observation. And what's really interesting here is that you're going to take a sequence of action rather than just one action, right? Which is slightly different from the, single step world model transition dynamics, because now you are actually taking K steps, right? So after you take K actions as a sequence, then you're going to predict the latent representation of the observation in K steps, right? So the way that you're doing it is through this contrastive loss, so that you're able to predict, given us at a time t, given the observation, given a sequence of action, what is the next state? Okay, after the sequence of action. And this is really nice in the sense that you're able to somehow learn a representation such that under this representation, you're able to do world model prediction very well. And what's even nicer is this kind of sequence of action that does this kind of suppressing of the compounding error we're all familiar with, right? Compounding error is this Lataris kind of era where things could blow away, things could blow up when your number of steps goes up, right? So because one deviation will take you somewhere nearby, but multiple deviations would take arbitrarily far. So this kind of predicting observation, latent K steps into the future using contrastive loss turns out to be really effective for efficient learning. I can show you some results here, but this is actually a series of work that we did in our lab, starting from SMART and then tackle, which is not a foundation model, but essentially is a proof of concept for this, kind of tackle loss. Then we finally did a more large scale work called a premium tackle, which actually built like a very, diverse trained model that is able to remarkably generalize to downstream tasks. Here I'm showing you the adaptation, from seen tasks to unseen tasks, from easy tasks to harder tasks, also from shorter horizon tasks to longer horizon tasks. So through this kind of representational learning, you're able to use the limited data you have from the environment to adapt to learn a model that is generalizable and resilient. So I didn't mention one thing, which is the resilience, right? So when I said resilience, I specifically meant to say that it is kind of resilient to low quality data. What I mean by that is not necessarily these expert demonstrations, but sort of some random exploration data. Well, so for world model learning, kind of inspired training objective, this is really, really nice because we all know that we don't need expert demonstration to learn the world. we just do random exploration to understand the transition dynamics, right? You do kind of like compounding error suppression, and using this contrastive loss, it turns out to be very effective to understand the world using even just random exploration data. That's what we mean by resilience. So this makes things very easy because we don't have to curate a lot of expert demonstration, which is very human laborsome. Okay, so some more results, few shots behavior cloning of some unseen tasks for DeepMind control suite, and for meta world, for 20 shots, 5 shots, well, actually for dog and humanoid is 100 shots because they're relatively more challenging. Now we also show you some liberal 5-shot behavior cloning results on these unseen tasks. You can see the premium tackle really is phenomenal compared with many of the baselines, including some of the state-of-the-art that people believe are the best representation learning methods. Okay, so as I said earlier, it is really robust to low-quality pre-training data, which is not surprising, right? Because it's a sort of like world model guided objective that we are using here. So now, I wanted to sort of think about again the small data problem, right? So we're in the small data regime for robotics. So one of the philosophy I really like, as just a personal take, is to reuse compute, right? So we have already trained all these foundation models for NLP, for computer vision, including vision language models, right? And they have a remarkable perception in the wild, right? So they've already used all the compute to train such big models. Can we reuse this compute rather than doing everything from scratch for robotics, right? And apparently, vision language models themselves are not sufficient for doing robotics or for doing sequential decision making. But can we at least utilize those compute that's already been used and try to improve them? And maybe infuse them with robotics capability or planning capabilities for sequential decision making problems, right? So that's the sort of idea. Sorry, let me put this here. Yeah, so that's the kind of idea behind this work we call kind of FLAIR. But before I introduce FLAIR, here is a review of some regular kind of vision language action models. Indeed, vision language action models are essentially a reuse of the compute from building these vision language models, right? In here, you fine-tune these vision language models using these question and answer pairs where the questions usually is like, the instruction of pick up the industry object and place in yellow bin or something, right? And then the action is exactly the next action you should be taking, right? So you just like fine-tune this vision language models to empower them with this kind of robotics capability. And here I'm just taking GR00T model from NVIDIA as an example here, but also Pi0 models that are very popular as one of the major VLA models out there. Well, so what they do, right? So they have some image observations at a specific time point. They have this language instruction of the objective, right? So they go through some encoder, right? So, tokenize things, and you can get some image tokens and some text tokens, right? So, and then you go through a vision language model, whatever it is, right? Choose your best vision language model or favorite vision language model. And then you're gonna also, get some latent representations as a result of this vision language model, these purple and the blue things here. Now, so now you're doing robotics. You have this robot states, right? So you could try to encode this robot states into some kind of state tokens, right? And then you could have some action tokens so that you can use some kind of diffusion transformer to predict the action based on some noisy actions, right? So can start with noise and then you can predict the actual action. So that's what usually these group models or Pi0 models are doing, using this kind of flow-based, which the previous presenter also mentioned, right? So you can do this denoising process to actually predict the action. Okay. So now what group does is essentially just empowering this with this kind of world model idea. So not only you're going to predict the next action, but you're also going to predict the future image token, right? So which is essentially a transition dynamics, or you call it world model, right? So this entire thing is essentially this approach. So let's zoom in here just a little bit. Now, so with this observation and this instruction and these multiple layers here, what you're doing essentially is to add this additional tokens that are the future image tokens. And then in this DIT part, right? So because of you have this future observation, you could just do some kind of future latent alignment and use that as an additional loss for training your model. And that's just so simple. And this is a way of empowering this kind of existing vision language action models to have this world model predicting capability. So it's a lightweight, it's a really lightweight way of empowering them to be able to have this world model prediction capability, right? So I'll show you some results, right? So get some SOTA multitask imitation learning performance, as you can see here. We also, were able to do some kind of humanoid table manipulation. As you can see, the performance is really interesting compared with policy-only baselines. And what's really interesting about the empirical experiments we did is this kind of joint training on human egocentric video data. So we know that data collection is really the bottleneck here, right? Much more expensive to teleoperated data collection. So if you are able to actually, benefit from just human egocentric data that is very easy and cheap to collect, right? Then so that you're doing the similar tasks, or essentially we're hoping that they're the same task, but with different camera views and different embodiment, right? So what's really interesting here is that with this kind of joint training of human egocentric video data, we see a benefit essentially for this entire pipeline. Of course, that for human collected data, you don't really have the action to start with. So, for the next action prediction, it becomes really like a void, right? But because you empowered this kind of future embedding, which is part of this world model prediction, it will allow you to do that alignment there. Even if you don't have the next action as a ground truth, you're still able to do that alignment for future embedding, which helps significantly for your training and make your data much more efficient to collect. Right, so here we show with human ego videos, the performance has a huge boost in terms of compared with no human ego-centric video, which is a very, very interesting result in my opinion. All right, so now I talked about foundation model for robotics, specifically an alternative of latent world model, right? So the idea basically, just to recap, was this observation going through this encoder, going through this action. You have a world model that is able to do the rollout and predict the future, maybe in the latent space, right? So that is more compact and easy to predict. Now, so this is one kind of philosophy here, that to do kind of latent representation learning, but a lot of people think maybe there is already some kind of interpretable representation that is out there for robotics. Or for example, robotics is all about doing something, right? So pushing chip back to the left, put can onto the table, or stir food, and this kind of actions, right? So it's a motion, right? So maybe this gives us an idea
what if we're able to do some key point-based symbolic representation to capture the trace of the motion, right? Of the object that we are interested in. So that's this idea. And basically, this idea gives us this alternative too, which is a symbolic representation world model on top of the symbolic representation, right? So what I'm really trying to say here is that, if you have an observation, if you're able to do some kind of symbolic representation extraction, for example, the trace of the motion, then you could potentially utilize that as the common space for your world model prediction, right? Which means that you're going to predict the trace of the next step given any action, right? So that, seems to be a different kind of philosophy that you're utilizing here for learning this world model. But how does that work? So it turns out we did some preliminary work was, just a concept of like improving the existing vision language action models. So that vision language action model have this initial state and final state, right? So it's a motion, kind of trajectory of the motion. So what we did is use this multi-point tracking, essentially find some key points. And then once you're able to find the key points that are moving the most, then you're able to just generate the trace of these key points, right? So you can generate this visual trace, which is representative of the motion. And now, once you generate these visual trace, as I say here, then you could do something really simple by just prompting a vision language model to be able to do prediction based on both the original image and the visual traced image, right? We call it visual trace prompting. So this idea, although very simple, seems to be very effective to improve the existing vision language action models, right? So why would it help? I guess, one thing is a really compact representation of the historical information rather than providing all the frames of the images in the history, right? You could potentially just use one image with the trace, which is already a very compact representation of the history. So I think that really helped for the visual trace prompting to work. And also this kind of, key point tracking and the, trace of the key points is a great compact representation for us to utilize the smallest bits to represent the largest information. So again, I think this is a spatial calibration in the sense that you're able to understand the space much better using these visual trace prompting. But this is not a world model prediction yet. This is just utilizing the historical trace as a prompting to help your vision language model to be better, right? So we're still, as we said, we're still in the small data regime for robotics. How can we make things better, right, with all these variations? So I sort of wanted to, talk about this concept of exploration, which is, a very long and traditional and, sort of like good old topic in reinforcement learning, right? So, but here I wanted to say, now that we have all these agents, right, these kind of foundation models as agent, can the model collect data by itself? And that's the kind of question I want to ask, which is related to exploration problem, but more about the agency of the agent being able to collect data by itself, right? So what do I really mean by that? So take this kind of human babies, right, as an inspiration that, when they were in a physical environment, right, so they do some kind of self-generated task goals. I mean, babies actually have very different task generation. I often cannot rationalize what they were doing, but somehow they have very determined goals that wanted to achieve, and it's self-generated for sure because they can't even talk yet. And they have some intrinsic motivation, which we probably don't understand as adults. And what about agents, right? So can agents also do this kind of like self-generated task goals and also have some kind of intrinsic motivation to explore the world? I mean, you could do like human guidance, but it's too expensive, right? Can we do something more kind of autonomously, right? So here, exploration RL is essentially doing that, but does it really work, right? So we have some methods of goal sampling methods or training an intrinsic reward model and these kind of things. Many of them works very well, but the reality is, also they work not so well in a lot of situations. For example, I'm showing you some failure cases of exploration RL that didn't really work. Okay, so now the real question is, how do we reuse compute? How can we utilize these already existing foundation models and empower them with this exploration capability? So take a vision language model as an example, right? So we know that is really powerful because it can do it can understand object semantics, right? So I can do spatial relation understanding. It can even predict the potential outcome of taking some actions into the environment, right? So with all these capabilities, maybe the question is, can we have a VLM-powered AI agent that does all the exploration of the world for us? Unfortunately, although it's capable of semantic understanding and planning, it's quite disconnected from a physical experience. I'm not going to show you failure cases here, but I think people all agree with me that vision language models are still not necessarily very physics grounded yet. So how do we really make sure that we can utilize such a VLM without ever, fine-tuning this vision language model to be able to have this physics grounded way of understanding, exploring, and planning in the world, right? So this is essentially the motivation of this work, which is called IVE, Imagine, Verify, and Execute, is a memory-guided agentic exploration with vision language models. So this is how IVE works, right? So you observe the environment, and then you have a scene describer of this environment. For example, you're going to say, hey, there are all these objects, and there's all these relationships about these objects, right? These can be represented as a graph or scene graph as nodes and edges representing the objects and the relationship of these objects. So now we have a memory module. This is quite important. With this memory module, what we're able to do is, empower this kind of explorer agent, which understands, what are the relevant scene graphs that are related to this current scene, right? And, they could even understand how far away these scenes could be, right? So with that, then the explorer can come up with a desired scene for me to explore as my next new scene that I'm able to collect into my memory, right? So, and not only that, maybe the explorer can also tell me what are the skills or the actions, the sequence of actions I need in order to transit to that new scene, right? So that's not the end because vision language models are not physically grounded. So we need a verifier. We sort of wanted a verifier to make sure that this kind of desired graph is achievable, right? The desired scene graph is achievable. So, you can use the verifier to give feedbacks whether this is not achievable because of certain reasons, or it is achievable. And here is the sequence of action. We call it a skill sequence to achieve this new scene, right? So then you have these action tools that we designed so that the robot could actually call the action tools to actually implement the sequence of skills and achieve the next observation. So overall, you can see this is an agentic framework with a memory module and interacting with the environment using this scene graph representation, which is symbolic representation, right? You have this explorer, you have this verifier, which makes sure that explorer explore the new scene, but also remain physically grounded, right? So this action tools is also quite important to make sure that this vision language model is well connected to the actuators, which is the robot arm. Okay, so we can show you some results very quickly. So here I'm showing the exploration scores. You can see you can see that IVE is really remarkable, sometimes even better than human experts, right? So in terms of being able to come up with new scenes, because those are not like very human intuitive tasks to explore. And IVE actually does very well given all these very highly curated action tools, and as well as like the memory module that is very compact. All right, so now I'm also trying to show you like some downstream tasks with this IVE collecting data. We're able to use the data collected to do some downstream tasks. For example, you can do world model prediction, right? And then you can see remarkably these world model prediction, IVE is almost achieving a human level performance and significantly better than previous state of the art. Now for goal-conditioned behavior cloning as another downstream task, you can see IVE actually achieve better than human performance, which is really impressive in my opinion. So what is the future? Just to recap what we talked about today. I sort of wanted to build a foundation model. I talked about how we can use world model to guide us to do more data efficient representation learning that are respecting world model prediction. Maybe suppressing compounding error and using contrastive loss is a great way going forward. But I also talked about reuse compute, that how can we reuse the existing kind of foundation models that's already trained on a lot of data and kind of infuse these foundation models with robotic skills. So what is the future beyond, right? I can go through this kind of latent representation, I can go through the symbolic representation. But one of the things that I'm super excited about is the synthetic data and self-improving direction that, essentially I think is the ultimate way of dealing with the small data regime problem, right? So if you're able to somehow, generate whatever your input space data is, and then you have a way of verifying what, your data generation quality is, right? Using some kind of world model, maybe some rules, maybe some kind of external verifiers, and somehow filter or curate your model. Filter your data so that your data is higher quality. And then you can feed back that data and use that data to improve your model and do this kind of self-improvement. So my lab has been doing some work related to that. And that's one of the directions I'm super excited about. Another thing I wanted to mention is, this kind of enhancing spatial temporal reasoning capabilities of multi-model foundation models. I personally think that spatial temporal reasoning capability is still the main bottleneck for computer vision, but also for robotics and sequential decision making. So we also did some work there. I won't talk about it today, unfortunately. And finally, last thing I wanted to mention very briefly is this kind of test time compute scaling, which essentially, not only for this math problems, but also for robotic planning, especially for long horizon tasks. I personally think that, although a lot of people talk about the latency of vision language action models, I feel like, efficiency will not be the problem in the future, just because we have all these advancements in hardware and in algorithmic efficiency and so on. But now, what we're really lacking is somehow this test time compute scale for robotics or for planning problems. And, that's also one of the things that my lab is currently working on. Okay, with that, I'm gonna just stop by the list of papers I talked about today. Thanks.
Thank you, Furong, for the amazing talk. I don't think we have time for questions. We are already running late a bit. So yeah, if anyone has questions, I think you can always reach out to Furong.
Yeah, thank you. Thank you so much for having me. Again, hope you have a great time there in person.
Yeah, thank you. See you.
See you.